Another example is the entropy change in free expansion. Again, if we look at the process that we have a gas here, we have a gas here, and there is a membrane that acts as a partition between the gas and the vacuum above. And somehow, if we break this membrane, the gas will diffuse. The gas will diffuse to the vacuum and eventually will fill the whole cylinder. The question here is that how can we calculate the change of the entropy in this process? The problem is that in this process, it is the irreversible process. It's an irreversible process. So, we may think that in this process, the free expansion, and if we seal the cylinder with the thermal insulator, so there is no heat enter or leave the system. But the problem is that even though we can say that the heat is zero in this process, but this is not the heat from the reversible process. Remember that when we define the entropy, we define the entropy from the heat that enter or leave the system in the reversible process. So it means that even though here heat is equal to zero, but the process here is irreversible. So we cannot say that dq is zero. We cannot say that dq is zero in this process. So what can we do in this calculation? What we want to do is that we will find the equivalent process that bring the gas from the initial configuration or initial state to the final state. The initial state is the state that the gas is in the lower part of the pistol with the membrane above that prevent gas to diffuse to the vacuum. The final state is the state that when the membrane is broken and the gas diffuse to the whole volume of the pistol and reach the equilibrium. From thermodynamics, we found that S is we call it the state parameter or the state variable. We talked about the state variable before, like a P, T, and V. S is the state variable. The state variable here means that the entropy, the value of the entropy depends only on the state of the system. It means that if the gas is here, in this state, the initial state, we don't care how the gas comes to this state. We don't care. Whatever the path that brings the gas to this state, we will have the same value of the entropy. And again, when we break the membrane and the gas diffuse to fill the pistol to the final state. During the process is irreversible, but we don't care. It means that after a while that the gas reach the thermal equilibrium to the final state, we say that the entropy of the final state will be the same, no matter that it comes from any state, the initial state here, by any process, reversible or irreversible. We just want to calculate the change of the entropy that brings the system from the initial state to the final state, whatever the process is. If we have the process that we can calculate the entropy, the change of the entropy will equal. It not depend on the process that we use. So in this situation, we can calculate the entropy change by find the part that bring the irreversible process that bring the system from this initial state to the final state. And in this example, we choose the isothermal process. We choose the isothermal expansion. Why we choose the type isothermal expansion? Because here we know that the temperature of the gas will be constant. We have discussed this before, because in this process the gas diffuse to the vacuum, there is no work and there is no heat because it is in the insulating wall. So it means that heat is zero in this process. Work is zero in this process. So it means that the change of the internal energy is zero in this process. If we can have any process that brings the system from the initial state to the final state and the internal energy of the system not change, it will give the same change of the entropy of this free expansion process. And if we choose the isothermal part, so the isothermal part, the temperature is a constant. So if the gas is an ideal gas, it means that delta E internal energy is equal to zero. So it's the same as the free expansion. Okay, the internal energy is zero. The internal energy is zero. Okay, so we will choose this part to calculate the entropy change during the free expansion, and we have that the change in the entropy is equal to the nR log of Vf over Vi. This is very simple to get this. We know that dq over T is equal ds is equal to dqr over T. Okay, and the change of the entropy is equal to the integral from the initial to the final state of dqr over T. But if we choose the isothermal part to represent, if we choose the part to calculate the entropy change as we have discussed before, because the internal energy is not changed. So it means that we can take t out of the integration. So this will equal to 1 over t of the integral of dq. But in this process, since the internal energy is 0, the internal energy is 0, so what we have is that the integral of dq is the total amount that enter the system. But the internal energy is 0, so it means that in this process q is equal to the work done on the system. Sorry, q is equal to the minus of the work done on the system. This is because the internal energy is 0. So we have q is equal to the minus of w. So we have that this is equal to the minus of w over t. W is the work done on the system. Okay, here this is the expansion. So the work done on the system is negative. So we must have that the minus of w is positive. And from the calculation that we have discussed in chapter 20, we can show that this is equal to the equal to the nRT of the log of Vf over Vi. You can see that this is correct because Vf is larger than Vi. So we have that log of Vf over Vi is positive. And for the change of the entropy, we have to divide it by T. So the final result is the nR of log of Vf over Vi. So this is the expression for the change of the entropy. You can see that since Vf is larger than Vi, we have the entropy change positive, which is reasonable. We can see that the initial state of the gas is more order than the final state. The initial state, all gas is below the membrane. So we can specify the position of the gas more precisely because we know that it is somewhere here and it's in the small volume under the membrane. But once you break the membrane, the gas diffuse through the vacuum above and fill the piston, fill the cylinder. So it means that it is less order because it can be anywhere in the cylinder. The initial state, gas can be here only, but the final state, gas can be anywhere in the piston, in the cylinder. So it's less order. So it means that the positive value of the entropy corresponding to the less order in the system.